and the actual count of intersections. And so dealing with these last two questions here, well, actually all three of them, comes down to a thorough understanding of what the asymptotic properties of this curve are. So let me start being a little bit more precise. I'll introduce this notion of a stable Hamiltonian structure. I assume it's probably not completely new to everyone in the audience, so I'm going to go through this pretty quickly. This is mostly just to establish my notation, but if I'm going too quick or something, please feel free to stop and ask questions. So I'll consider an odd dimensional manifold, and it'll be equipped with a pair. I'll denote the pair by H, lambda omega, where lambda is a 1 form and omega is a 2 form on M, and they'll satisfy three properties. So the first is that lambda wedge omega to the n is a volume form. Okay, so what we get from this is that locally, at any point the tangent space decomposes into, this tells us that omega is full rank, so the kernel of omega, or the kernel of the map V maps to that, is a line bundle. And then we get this hyperplane distribution, which I'll denote by CH, which is the kernel of lambda, and that is always transverse to the kernel of omega. So locally we get at each point we get a splitting of the tangent space into this line bundle, kernel omega plus CH, which is kernel lambda. And so we can pick a preferred section of this line bundle. Lambda will always be non-vanishing on that line bundle, because this is the kernel transverse to it. And so we can pick a preferred section, XH, which is defined by the property that it contracts with omega to be 0. It's in the kernel of omega. And that it's normalized when we contract it with lambda to 1. So really I can get rid of this and write like that. And there's a couple more properties here. If we require that omega is closed and that d lambda vanishes on kernel omega, then it turns out that the flow of this vector field, we'll call this the Rave vector field, that the flow of SH preserves the splitting. With all additional structure too. So it should be pointed out that omega restricts to a non-degenerate 2 form on the hyperplane distribution, so it's a symplectic vector bundle, and the flow of this actually preserves that splitting with all additional structure. So there's three sort of major classes of examples of this. The first is contact manifolds. So lambda is a 1 form, a contact form, which means lambda wedge d lambda to the n is a volume form. So our stable Hamiltonian structure would just be lambda comma d lambda, and in this case we get the normal Rave vector field defined in the contact world, and this hyperplane distribution is the contact structure. Second important class of example are mapping tori of Hamiltonian flows. All right, so our manifold will be S1 cross a symplectic manifold. and we can put a periodic Hamiltonian on the manifold. And the stable Hamiltonian structure here, we take lambda to just be d theta, where theta is the variable in S1, and omega to be, I'm not sure if I want a minus or a plus there. It depends on how you define the Hamiltonian vector field, right? There's always a disagreement about that plus minus. But if we look at this one form, then the Rabe vector field of this stable Hamiltonian structure is just d theta plus the Hamiltonian vector field. So this gives us the flow of this Rabe vector field gives us the mapping torus of the Hamiltonian flow. And this example we'll use later. When I mentioned I'd construct an example of an intersection disappearing out at the end, it'll be in this case. Final example are principal S1 bundles. Over symplectic manifolds. So I've got some M over some symplectic manifold, and so omega in the stable Hamiltonian structure is just the pullback of the symplectic form to the bundle, and then lambda will be a connection form on the bundle. Okay, and in this case, the Rabe vector field is just the infinitesimal generator of the S1 action. And the hyperplane distribution, the kernel of lambda, is just the horizontal distribution determined by the connection. Okay, so it's been, let's start here. We want to talk about pseudo-holomorphic curves in cylindrical manifolds over these things. So we can define given a stable Hamiltonian structure, lambda omega, we can talk about compatible almost complex structures. So what this will be is we first choose a J as it's an endomorphism of this hyperplane distribution that squares to negative the identity. And then we can define an almost complex structure on R cross M, define an R invariance by requiring, let's name it, R invariant almost complex structure J tilde, by requiring that J maps the vertical direction to the Rabe vector field of the stable Hamiltonian structure, and that J restricted to the not contact structure, this hyperplane distribution, or the pullback of it to R cross M, is just the complex multiplication we chose on there. All right, and result that goes back to, I guess in this case, this goes back to Fleur theory. In the contact case, it goes back to, I don't remember what year Fleur was, but let's say late 80s. In the contact case, these things were studied first by Hofer in 93. One can study pseudo-holomorphic curves. So we take a closed Riemann surface and take out some finite number of punctures, some finite number of points, so a finite set, and map this to R cross M with this almost complex structure. And there's a notion of energy. I don't really want to talk about what energy is, but there's a notion of energy for which finite energy implies that these things are asymptotic to periodic orbits. Near non-removable punctures. Okay, so I expect most of that is at least not completely foreign to this audience. So now I want to get into talking about these hypersurfaces, or not hypersurfaces, these submanifolds I'm interested in studying. So we'll say a submanifold V of a stable Hamiltonian manifold M. M will be equipped with that lambda and omega, is a stable Hamiltonian. Let's abbreviate that, stable Hamiltonian submanifold if, I haven't finalized my notation here, maybe I want to call this a strong one. If two conditions, the pullback of this 1 and 2 form to V is a stable Hamiltonian structure on V. I think that's probably the correct thing to call a stable Hamiltonian submanifold. Strong would be that the Rabe vector field in the ambient manifold is tangent to V. So that V is invariant under its flow. Or in particular, this should imply that the Rabe vector field, I can pull this data back. If it's a stable Hamiltonian structure on V, I get a Rabe vector field there, which of course is tangent to the submanifold. That those two things would agree under this condition. Okay? And I'll mostly be interested in the case that V is codimension-2, but a lot of what I say about the intersection properties would apply to any dimension. But let's look at several examples. I want to consider, let me just go through several different examples that show you how these things tend to arise quite naturally. So in the contact world, there's the notion of a contact submanifold. Which almost agrees. So I've got M with a contact structure, which is the kernel of some contact form. And if I have some submanifold, I'd want this to be a contact form on V. Okay, and then it's a strong contact submanifold if the Rabe vector field of lambda is tangent to V. Okay, and given a contact manifold, a contact submanifold rather, this property that the Rabe vector field is tangent to it can always be arranged by multiplying lambda by a positive function. Okay, there's various neighborhood theorems here, so you can just pick a model case and look at the normal bundle and find one example there, and then there's always some Moser arguments that let you arrange this. All right, so let's actually get into some more, within that world, some specific examples. Just trying to convince you this is a notion worth studying. So there's open book decompositions. So in this case, I'll have M, a contact manifold, and V, a submanifold, a possibly disconnected submanifold, and M minus V fibers over S1. And d lambda restricted to a fiber is a symplectic form. Okay, so these play a very important role in contact topology, understanding the structure of contact manifolds, both in 3 dimensions and higher dimensions. Let's see, how else do these arise? Unit cotangent bundles of Riemannian manifolds are contact manifolds. Okay, and the Rabe flow of the contact manifold gives us geodesic flow of the base. So here, there's a Riemannian notion of a totally geodesic submanifold. Let's just abbreviate that. Totally geodesic submanifold. So if I have a totally geodesic submanifold in the base, it actually lifts to a strong contact manifold in the unit cotangent bundle. So we sort of see these things come up topologically, and in the Riemannian world, they arise geometrically. In algebraic geometry, we can consider a complex polynomial on Cn and look at its zero set. And if we're away from critical points of that polynomial, the intersection, so I get, let's f of z equals 0, I can intersect this with the unit sphere, or a sphere of any, round sphere of any radius in Cn. And this intersection, if transverse, is a contact submanifold. Of S2n minus 1. And as I mentioned earlier, that can always, by changing the Rabe vector field a bit, I didn't actually say what the one form is there, but by changing that a bit, you can arrange for this to be flow invariant. And then let's see. Finally, there's some dynamical examples where these things come up. Do I have room here? So there's a notion given contact manifolds of a connected sum. So you can always form, if you have 2 contact manifolds, M1 and M2, let's call it, we can form some contact connected sum. I should have drawn that bigger. And so within the connected sum, there's this sphere here. Let's say this is 2n plus 1. That's S2n. And one can check by looking at these models explicitly that the equator here of that sphere, so when S2n minus 1 is a contact submanifold. Okay, and there's certain dynamical systems where these actually arise quite naturally as flow invariant submanifolds. So for example, in the spatial restricted three-body problem. So the way that works is I've got two massive primaries, two massive bodies, and I choose a coordinate system so they're fixed. And now I'm considering a third body that's traveling in their gravitational field in 3 space. One can write down the Hamiltonian for this, and there's a critical point that, at least in position space, lies between those two bodies somewhere. And if you look, that's sort of that's the smallest critical point. So below, for low energies, you're either traveling in a compact region around one primary or traveling in a compact region around the other. As you cross this now, the energy increases, you can now move back and forth. And so there's a contact structure one can put on this, and this looks like a contact-connected sum. And one can check that for energies just over that critical point, there's actually a flow invariance S, in this case it would be S3, in that neck. So dynamically, these things arise quite naturally as well. How am I doing on time? Okay. So that's in the contact world. There's one final sort of example I want to mention. Important is in this principal S1 bundle picture. If I have a codimension-2 symplectic submanifold here, and I look at its preimage under the, or its lift to the bundle, I actually get, again, a flow invariant codimension-2 stable Hamiltonian submanifold. Okay, and so these arise, such submanifolds arise in Gromov-Witten theory. There's a relative Gromov-Witten theory. And a symplectic sum formula. Due to, there's different versions of this, due to Ian Allen Parker and Lee Ruan. And there's some dispute over the correctness of this work. You can look at a preprint by Tarani and Singer where they mention their disagreements, but the details of that aren't important to me. What is important is that there's something there that should be true. And so in this situation, we'd have two symplectic manifolds. Let's call them sigma 1 and sigma 2. And then we'll have a codimension-2 symplectic submanifold that are symplectomorphic, and I want to assume their normal bundles have opposite Chern classes. And so then what you can do is actually remove these guys and form what's called a symplectic sum by just taking those fibers and doing something in each fiber that looks like a connected sum. Okay, so if you lift that, or more generally, one could picture doing that in the stable Hamiltonian world. If I've got a two stable Hamiltonian submanifolds and codimension-2 submanifolds, and they're whatever the appropriate notion of diffeomorphic is, and they've got compatible normal bundles, one could actually do this construction and hope that there's some relative version of symplectic field theory and some symplectic sum formula that generalizes this one. And I should mention in this picture, there's a correspondence between Gromov-Witten of the base and SFT of the bundle. So if I've got a symplectic submanifold and I study Gromov-Witten of the base, holomorphic curves up here are just pairs that consist of a holomorphic curve in the base and a meromorphic section of the bundle. Okay, so if one can come up with a correct notion of relative SFT relative to these things in a symplectic sum formula, it should contain this as a special case. Okay, so hopefully, after that long aside, I've convinced you that these things are worth studying. And in particular, in the cases where they arise, one might be able to put interesting additional structure on SFT by considering a filtration. One thing I neglected to say is this flow invariance tells me for any compatible J, this thing's at least close to being J holomorphic. These, so if I've got M and then V inside, the vertical direction gets mapped to the Rabe direction. So I just have to consider the J on this hyperplane distribution. So we can always choose a compatible J so that R cross V has tilde J invariant tangent space. Okay, we would just look at the intersection of the hyperplane distribution with the tangent space to V and pick it there, and then pick it also on the symplectic normal bundle within that hyperplane distribution. So this can always be arranged. And now the question is, I'm very far away from even having a guess of what the right theory would be, but can we put extra structure on SFT by filtering, let's say, filtering by intersections? Right, we have intersection positivity, so we might hope we get a nice filtration by counting intersections of the curves with the submanifolds. And long term, can one possibly prove some sort of symplectic sum formula? Okay, and so as I mentioned, there's some technical difficulties here. Coming from the non-compactness. So I won't write them down again, but first, finiteness is not clear of this intersection number. I could have a sequence running off to infinity if the curve doesn't live in that submanifold, but it's got an end that goes to an orbit in that submanifold. Topological invariance is a problem. I can lose intersections at the end. And so I want to figure out, how can I deal with this? Can I define some product that tells me how many intersections there should be there? So to do that, I want to look at a very concrete example, one where you can actually write down the flow quite explicitly and write down the curves explicitly and actually see an example of this thing running out the end. And if one can say, in general, we get enough understanding of the behavior of the curve that's the same sort of thing can happen, then we can actually, we know how to do it. So here's an example. Let's pick your favorite closed symplectic manifold. And we'll put an autonomous Hamiltonian on it. And now I want to consider the symplectic manifold R2 cross W with omega naught plus, I'm going to be sloppy about writing the pullback. Let's call that omega W. So the standard product symplectic structure on there. Okay, and I'm going to put a Hamiltonian on this. I'll call H alpha, which is 1/2, put an alpha there, 1/2 x squared plus y squared plus HW, or really the pullback of HW. So I've got a Hamiltonian flow on W, and then the flow, or at least its behavior when restricted to this R2 factor, is just twisting. It's a radial Hamiltonian, so I get twisting. Use this board. So, the Hamiltonian vector field. Yeah, alpha's yeah, a real number. And later I'm going to, for the sake of getting non-degenerate periodic orbits, I want to assume it's irrational, or at least irrational when scaled by 2 pi. The ray vector field, or the Hamiltonian vector field rather, is alpha minus y dx plus x dy plus this on the w factor. So periodic orbits, this thing, as long as alpha is irrational up to scaling by 2 pi, never, at least as it has 2 pi. Let's say I want to consider this. So stable Hamiltonian structure, when I'm looking at the mapping torus here. It's an autonomous Hamiltonian, but let's look at the 2 pi mapping torus. And so then, if I call t the coordinate there, I get this. And so periodic orbits are, as long as the alpha's 2 pi irrational, let's say, this thing only never has any periodic orbits except for its 0 here. So we get periodic orbits are things of the form S1 cross 0 cross rest points of the Hamiltonian on W. Well, so it's an autonomous Hamiltonian. So if I ignore the 2 pi parts, it should just be, I guess, like periodic orbits also of the right period would be okay, but yeah. So I guess those aren't the only periodic orbits, but those are some periodic orbits. So now I want to put an SFT, almost complex structure, on this. So and so what we'll require is that on W it's just some compatible almost complex structure. On the R2 component, it should be I or J naught, the standard complex multiplication. And then here what should happen? The first component should go to the ray vector field. So I get an I there. I'll call this delta xy and gamma of W rather, where delta xy is this, and gamma of W is the Hamiltonian vector field of HW, and then minus J there. And now what I want to do is consider a map of the form ST in R plus cross S1 to R cross S1 cross R2 cross W. Okay, and so ST will map to S comma T. I'll call the components in R2H and the component in WK. So actually I should point out I get a stable Hamiltonian submanifold here, codimension-2. V, which would be S1 cross 0 cross W. Okay, and so I want to understand intersections of this map. I'll call this map U. Intersections of this map with this codimension-2 submanifold. There really are crosses. Well, so to understand that, I claim the intersection number is equal to the count of zeros of H, where H is that transverse component. Okay, that's not too hard to see. And so now the question is, what can we say about H? How does it behave? Well, if I look at the J holomorphic curve equation, H satisfies HS plus IHT, and then let me check my sign here, plus alpha H equals 0. Okay, I can just take S and T derivatives of this and plug it into the J holomorphic curve equation, and the H component is going to go right across here. And so this is where I get that from that delta, that alpha H term. Okay, so this actually looks like an ODE if on a loop space, right? This is like ds minus A of H equals 0, where A is the operator minus I dt minus alpha. So we can write down solutions to that explicitly. H is of the form, I get e to eigenvectors of this operator times S times eigenvectors. So what are the eigenvectors? They're the same as if I get rid of that thing. So the eigenvectors look like that. And eigenvalues are integers. Without this, it'd be integers. Putting that in shifts them by alpha. Do I want a plus or a minus? I think I want a minus. So I get this explicit formula. And if I want this thing, as s goes to infinity, to converge to 0, then I only want to look at k. I want this thing to be negative. So k should be less than alpha. Okay, so let's look at a specific example of a k. I know, or of such a curve. So let's say that h is equal to, I'll put a factor in there. Epsilon, we'll say alpha is between -1 and 0. That's not so important. With an epsilon in front of it, and then another term. This is just, anything I write down of this form will be a solution. And now I want to count the intersections. Well, the intersections of the curve where I put that h epsilon in there, with that hypersurface is the count of zeros of this guy. And that in turn, this is a map from a cylinder to R2. I can compute that by saying winding of h epsilon s for s large minus the winding when it's 0. So let's compute the second term first. The winding at 0 is what? Well, epsilon could be anything. Let's say it's small. So small so that this term, -2, when epsilon's equal to 0. All right, so what's the intersection number? Or what's the count of zeros here? In one case, when epsilon is not 0, I get -1 minus -2, or I get 1. From small to 0, I've got an intersection here that disappears out the end. Okay, but it's traded for something sort of quantifiable at the end. Namely, there's some sort of notion I can look at this and say, these things are giving me some measure of sort of normal tangency to the hypersurface. Right? And so when this leading term disappears, right, this intersection's disappeared at the end, but it's been swapped for now having a higher degree of tangency at infinity. Okay? So another way to look at that, I'd mentioned relative intersection numbers earlier. I could take this curve, u epsilon, let's call it, which is st h epsilon k, and define a perturbation where I push it by a small epsilon, let's say epsilon's in C, which confuses some people sometimes when I give this talk. Just push this a little at the end. And now this thing's got a well-defined intersection number. What is the intersection number? Well, it's winding of S large minus winding S equals 0 of H epsilon S comma dot minus or plus epsilon prime. Right, same sort of counting argument works as before. So if S is really large, this thing goes to 0. I get epsilon, which has got 0 winding. So I get 0. And if S at S equals 0, as long as I pick this small enough so that this is the dominant term, you know, when I do this perturbation, I don't want to introduce any new intersections down here. So I just put that, or I could put a cutoff function, whatever, you know. I still get the minus 2 there. So I get 2, regardless of the value of epsilon. There's 2 intersections when I do this perturbation. Okay? And so what doing this perturbation does is it ends up actually introducing a new intersection. Non-zero, I've introduced 1 intersection here when I did this perturbation. If it's 0, I've introduced 2. Okay, I could perturb in any direction I want. And the number of intersections introduced will depend on that perturbation. But the key is there's some minimum. The number of intersections introduced is minus the winding of H epsilon S for S large. Okay, you can check that explicitly in these cases. And so if I want to define a nice topologically invariant intersection number, that gives me some information about how many intersections there should be there. What I'd want to do, let's call this U star V. I can compute the intersection number of the perturbed curve U with V, which gave me, I get some count of intersections in the middle and what I've introduced by doing this pushing. I say the reasonable thing to do is subtract off the minimum of what you have to introduce by doing this pushing. So what you introduce is minus the winding. The minimum is going to be the maximum winding of one of these eigenvectors, which in this case, if I cut off between -1 and 1, is 0. So I want to say I want to subtract off -1 there. No, I want to add it on, actually. And so I always get 2 minus 1 equals 1. So the right way to count this, maybe this is confusing, but over there, I say the right way to count it is in one case there's an intersection, and if I look asymptotically, nothing can come in at the end. But this guy can disappear at the end and be traded for some higher degree of tangency at infinity. And so I want to say, really, that intersection is still there. It's just hiding at infinity. It's swapped for something that's quantifiable about the asymptotics. Okay, so I got not so much time left, but my claim is, any questions about this setup? I mean, it's very, you could give this to, advanced undergrads. It's just a zero counting argument with some winding, but the question is, in a more abstract setting, how do we interpret these things correctly? And there should be a sanity check too. So for instance, I had this case where the Gromov-Witten of the base corresponds to SFT upstairs. In that special case, whatever sort of intersection number I want to define, I could project everything downstairs, and I've now got a closed curve and a codimension-2 hypersurface, and that's got a nice, well-defined homological intersection. If whatever I define should, in that one special case, when I project down, actually correspond to the homological intersection number, right? If I'm speaking sanely.
So if I were to rephrase what you say, given any curve, there may be some intersection that's hiding at infinity. I mean, in this situation, there was none for epsilon different from 0, but there was one for epsilon equal to 0. And you say, given any curve, you want to perturb it in such a way so that that intersection becomes visible. And that's the purpose of introducing this epsilon phi.
Yes.
Yes?
Mm-hmm.
So you say for any what the intersection is. You will only be able to say an approximate sense of it someday.
Yes.
Yeah?
Yes. But I do get an upper bound, right?
Yeah.
The one, I mean, there's issues down here because there's a boundary down here, but as long as I keep that boundary fixed, the one gives me the upper bound. And so the key to generalizing this to more broad settings is an understanding of the transverse asymptotics here. So I don't have much time, but let me just give the setup. I'll do this mostly with pictures. There's M, there's V, and I got some curve that's coming into a periodic orbit in V. So a theorem, which will appear hopefully in 17-ish, is, let's call this guy U. And let's say this is codimension-2. You can do it in any other codimension. You still get the same formula for the transverse asymptotics, but it's now no longer has a winding number. It's just some eigenvector. I mean, in general, there's some operator here that's measuring the linearized flow, and our assumptions say it splits nicely. And so there's this formula. Let me simplify my theorem by saying this. The transverse, so let's actually just identify a neighborhood here. Take a tubular neighborhood and identify with a neighborhood of 0 the normal bundle of V. Right? So then I've got a well-defined tangential component. I can project the curve down to V, which gives me the tangential component, and then the normal component is a section. The asymptotics tell me that essentially this will give me a section. So the transverse component, let's call it UN, or not transverse, transverse or normal component, has a well-defined, I have to pick a trivialization around the orbit first of the hyperplane distribution, or just the normal part, a well-defined winding number bounded above by, I take what I'd call the normal Conlete-Sander index of the orbit over 2, divide by 2, and take the greatest integer. So the normal Conlete-Sander index is either I look at the linearized flow and just restrict it to the normal bundle, or alternatively, I've got a periodic orbit in V. It's also a periodic orbit in M. I can look at the Conlete-Sander index in M and the Conlete-Sander index in V and take the difference. That's the normal Conlete-Sander index. Okay? That will depend on some choice of normal trivialization, but so does this winding. This winding is always bounded above by this, and the difference is independent of trivialization. So let's say winding of U normal is bigger than or equal to 0. Okay, so that tells you that in general, you do enough analysis and you get that this example tells you the thinking in this example transfers to the general case. Okay? You get some notion of tangency at infinity by looking at how big this winding is. And so then there's a theorem. I've got how much time left? 3 minutes, just enough time to state the theorem. Or I guess I have to state a definition and then a theorem. So definition, that's the same assumptions here. I've got a curve. I've got this stable Hamiltonian hypersurface and a curve. I should say this can be generalized a bit. I can let my J not just be R invariant, but converging to something that's R invariant. And in higher dimensional SFT, if I want to get transversality, I'm going to have to allow some inhomogeneity, some perturbations. And one can define a notion of a perturbation compatible with this hypersurface. I need the normal component to vanish along the hypersurface. As long as I do that, I still get positivity of intersections and this being positive. So what I want to do is define an intersection product between that map and the hypersurface. And I do it like I did over there. I first perturb U by picking some trivialization of the normal directions along all orbits and pushing this guy and computing an actual intersection number. And then I add on this term. So all the punctures, I want to look at the normal Conley-Sender index of the asymptotic limit at that puncture and do this. And the theorem says this product is finite. That's pretty obvious. Topologically invariant. So it just depends on the relative homotopy class of U with the ends fixed. And you can compute it as the actual count of intersections of U and V plus what I'll call delta infinity of U with V, which is you look at these normal windings at the ends and the difference between that and their extremal value gives you some count which I would call the asymptotic intersection number. And this intersections number is equal to their sum. Okay? Both things are positive, or not positive, non-negative. And neither one is topologically. A family of curves, if I homotop U, each of these things could change, but this is topologically invariant. So the moral of the story is intersections disappearing out the end only get traded for these flips in normal winding at infinity. So one can count these and you come up with a topological upper bound on the count of intersections. In particular, if this quantity is 0, you know this curve doesn't intersect that hypersurface ever. Okay, and it's got nice properties of adding up well. And this, I was assuming non-degeneracy here, but one could consider more spot case and generalize this appropriately with the right generalization of the Conley-Sender index. And that's important because that one case I mentioned of the principal S1 bundles is more spot. Every fiber is a periodic orbits. But this intersection number, if you define it the way I have here, and then project down to the case where you've just got closed curves in a closed submanifold, this will correspond with the homological intersection number. So it's sort of the same thing you'd want it to be in the, let's call it, classical case. So I will stop there.